Hello and welcome to this revision session on AQA GCSE Physics Paper 2 for Separate Science. So in today's revision session we're going to be looking at how to answer examination questions from GCSE Physics Paper 2. So if we've been successful and learned in this revision session, we'll be able to answer GCSE Physics examination style questions so you can assess your understanding on GCSE Physics and then understand what topics you need to improve upon for your GCSE Physics. So how should you carry out this revision session? Well, when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and on this left hand side write down any working out or answers to the questions in the revision session. And when you're doing this, make sure you write out in full sentences and show your full working out, whilst in the right hand side in this section write down any pieces of information you find useful or any hints and tips on answering questions from this revision session. And at the end of the revision session, write up these notes into a revision sheet for you to use independently. So let's have a look at some questions, including our first topic, which is forces. So a student investigating acceleration uses gliders and air track and light gates. The air track reduces friction between the glider and the track to zero. Figure 1 shows the apparatus. The glider was released from rest and moved along the track. The mass holder hit the ground before the card passed through the second gate. So which two statements describe the effect this would have on the glider? So pause the video now, then unpause the video when you want to go through your answers. Right, so you've got to think about what is going on. So when the mass holder is released, it's going to be providing a force on the glider and the card. So what this means is it's going to cause the glider and the card to accelerate. However, when it hits the ground, that force is no longer present. So as a result, the resultant force acting on the card will be no longer present because that mass holder has hit the ground. Now we know that force is directly proportional to acceleration, or I should say resultant force is directly proportional to acceleration. So if the resultant force decreases to zero, the acceleration would also decrease to zero. The next question is, the mass holder should not hit the ground before the card passes through the second light gate. Suggest one way that the student could stop this happening. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to look in this situation at the information given in figure 1. So think about how you could alter the apparatus shown in figure 1 to ensure that the mass holder does not hit the ground before the card passes through the second light gate. So think about the two possible answers you could have. You could either shorten the string length, so as a result it would take longer to fall and hit the ground, or use a taller table, so as a result it would take longer to hit the ground, or you could move the two light gates closer to each other, so therefore there's a shorter distance for the glider and card to travel through before it hits that second light gate. Always use the information in the question to try and answer this question. So the student then increased the resultant force acting on the glider by adding more masses to the mass holder. She calculated the acceleration of the glider for each resultant force. Each test was done 3 times and table 1 shows the results. So the student made 2 mistakes in the mean acceleration column. Identify the mistakes the student made and suggest how each mistake can be corrected. Then write a conclusion for this investigation using the data in the table. So pause the video now, then unpause the video when you want to go through the answers. Right, so when you're having to critique mistakes in the mean acceleration column, you're going to have to think about 2 things really. You're going to think about how the number of decimal places or significant figures used, and then if they've calculated the mean value correctly. So you can see straight away that in that top row, for 0.20 newtons, the mean acceleration is given to how many decimal places there? 5 decimal places or 6 significant figures, whilst every other value is given to 1 decimal place or 2 significant figures. So therefore we know that is a mistake in the actual writing down of the results. The second thing is to check if they have calculated the mean correctly, which is done by adding up all the values and dividing by the number of values which are present. Now, as well as that, you should always discard anomalous results. So if you look at this, we look across in that first row, no anomalous results. Second row, no anomalous results. Third row, no anomalous results. fourth row, no anomalous results, but in that fifth row, there is an anomalous result of 7.2, but that was not considered in the mean calculation. So as a result, they should have recalculated that value. Now, what conclusion can you draw? Well, if you look at the data, you're going to have to look at the values of mean acceleration against the resultant force. Now, it's important to note that it's a bit too vague to say as one increases, the other increases, which it does. You've got to try and look to see if it's a directly proportional relationship, which is if one doubles, the other doubles. Now, we can see that roughly by looking at two values where one is double the other. So, the best one to probably use is either 0.2 and 0.39, because 0.2 doubled is 0.4, or 0.39 and 0.78, which is exactly double. 0.78 is exactly double of 0.39. So when we look to 2.6 doubled is 5.2, and 0.78 gets 5.1, which is approximately double. So we can therefore say that the force is directly proportional to the acceleration. That means you could say the larger the resultant force, the greater the acceleration, but it's better to see if there's a directly proportional relationship there. Next question. Figure 10 shows the horizontal forces acting on a man swimming in the sea. Describe the movement of the man when the resultant horizontal force is 0, and then the man increases force A. Explain what happens to force B and to the movement of the man. So pause the video now, then unpause the video when you want to go through your answers. Right, so the first thing to note is that what's the movement of the man when the resultant horizontal force is 0 newtons. Now, it's important to know that from the picture, it's clear to see he's already moving. He's already got a velocity. Now, a resultant force causes an acceleration. So if there's no resultant force, which it isn't because it's 0 newtons, therefore there's no acceleration. So therefore, the person is staying at a constant velocity or a constant speed, but they are not stationary because it's the idea of inertia. If there's no resultant force, an object which is moving will stay moving at that velocity, but if an object is stationary, it will stay stationary. So you've got to look at the situation. Now, the man increases force A, what happens to force B and to the movement of the man? So when force A is bigger than force B, there's going to be a resultant force in the direction of A, so the man will accelerate. But because he's moving through a fluid, in this case water, this means that the drag force will increase, because the faster the person is moving through the fluid, water, the more water particles they've got to move out of the way every second. So this tells us that the drag force B is going to increase and increase again until force A equals force B. At that point, the resultant force is once again 0, and so the man in this case moves at a higher constant velocity. Note, not terminal velocity, because the person isn't falling, they're swimming through the fluid. Next question. Figure 8 shows the forces acting on the kite. This kite is not moving. Identify forces A and B, and then a person flying the kite concludes the resultant force on the kite is 0. What is the evidence for this conclusion? The string breaks, which means force A is no longer acting on the kite. What will happen to the kite as a result? So pause the video now, then unpause the video when you want to go through your answers. Right, so first thing to note is that force B is acting directly down from the centre of mass of the object. So it is going to be the weight or the gravity of the object. Now force A is caused by a string being pulling on the kite. Now a pulling force is normally called a tension. So as a result, we've got tension as force A and weight as force B. Now what evidence do we have that the resultant force on the kite is 0? Well, once again, a resultant force causes an acceleration. F equals ma. So if there's no resultant force on the object, there's no change in the velocity of the kite, which is true because the kite is not moving, it is stationary. Because if there was a non-zero resultant force, if there was a value for the resultant force, the kite would accelerate. Now the string breaks, and this means force A is no longer acting on the kite. So there's only force B. So as a result, there's now a resultant force acting on the kite. So the kite is going to accelerate, and it's going to accelerate in the direction of the resultant force, which is downwards. Next question. A child drops a ball. The ball hits the ground and bounces. Figure 1 shows that the velocity time graph for the ball from when the ball is dropped until the ball hits the top of its first bounce. Air resistance has been ignored. When the ball hits the ground, energy is transferred from the ball to the earth. Explain how the data in figure 1 shows this energy transfer. So pause the video now, then unpause the video when you want to go through the answers. So this is an example of work being done, energy being transferred, which is caused by a resultant force acting on our ball. Now you've got to use your data in the question to show why work is being done, why energy is being transferred. Now the easiest way to look at it is either to consider the velocity at B and at C. So you'll notice that just after the bounce, the velocity is less than it was before. So you notice at the point where it's bouncing, now you can tell it's bouncing from B to C because it starts with a positive velocity at B and ends with a negative velocity in C, indicating to us that it must be moving in opposite directions, because plus and minus velocities in physics tell us the object is moving in different directions, which is what happens if it bounces off something. Now at B you can see that the velocity is higher than it would be at C, so the height at the top of the bounce is less than the height from which it was dropped, so the ball has therefore lost energy. So what has happened is that the energy has not disappeared, the energy has not been deleted from the universe, rather the energy has been dissipated to the surroundings. So the total energy of the ball and the earth and the surroundings is the same, but the energy has left the ball and gone to the surroundings. Work has been done. Let's now have a look at the topic of waves. So let's have a look at the following question. A car aerial receives radio waves from a radio transmitter. Radio waves are transverse waves, sound waves are longitudinal waves. Describe the difference between transverse waves and longitudinal waves. The radio waves have a frequency of 4.8 times 10 to the 9 Hertz. The wave speed of electromagnetic waves is 3 times 10 to the 8 meters per second. Calculate the wavelength of the radio waves, giving you answers to 2 significant figures. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to learn the definition between transverse waves and longitudinal waves. So in a longitudinal wave, the oscillations or vibrations are parallel to the direction of energy transfer or propagation, whilst in a transverse wave, the oscillations and vibrations are perpendicular to the direction of the energy transfer to propagation. It's very important you can state what is perpendicular and what is parallel for longitudinal transverse waves. It's always oscillations to energy transfer. Now in this next question you've got to know the equation, which is that wave speed is equal to frequency times by wavelength. Now once again, AQA like it if you write out the equation without rearranging it and then pop in the values to show that you know what the values are and then rearrange afterwards. So 3 times 10 to the 8 equals 4 times 10 to the 8 times by 9 times by lambda. So therefore lambda must equal 3.0 times 10 to the 8 divided by 4.8 times 10 to the 9, which is then lambda equals 0.0625 or 6.3 times 10 to the minus 2 meters in standard form. Now notice we had to write it to 2 significant figures. Now you start counting your significant figures with the first non-zero value. So the 0.0 doesn't count because that's not the first non-zero value. So the first non-zero value is 6. So you go 6.25, but the 5 will cause the 2 to round to the 3, so it's 0.063. Now the last thing you should therefore do in a question is therefore check to see if the answer looks sensible, and that looks about right for the values given, so it's going to be correct. Next question. Describe how the radio waves reaching the car aerial produces signals in the electrical circuit of the car radio. So pause the video now, then unpause the video when you want to go through your answers. So you've got to understand how car aerials and radio waves link to each other. So the car aerial absorbs the radio waves. This will cause the electrons in the car aerial to vibrate. Now a vibration of electrons backwards and forwards is an alternating current. Now the radio wave will cause the alternating current, the electrons vibrating backwards and forwards, to do that at the same frequency as the radio wave itself, which is a very important key fact you've always got to mention in these types of questions. Next question. Some types of waves are longitudinal and some types of waves are transverse. Describe the difference between longitudinal and transverse waves. So pause the video now, then unpause the video when you want to go through the answer. Right, so again, it's very, 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 very important you can learn the definitions of these waves. So in a longitudinal wave, the oscillations or vibrations are parallel to the direction of energy transfer, whilst in a transverse wave, the oscillations are perpendicular to the direction of energy transfer, which is very, very important to do. Now, next question. A group of students investigates the features of waves, and figure 9 shows some of the equipment they use. So write down the equation which links frequency, wavelength and wave speed. And the student wants to determine the wave speed of the water waves in the ripple tank. So describe a method the student could use. So pause the video now, then unpause the video when you want to go through your answer. So once again, it's very, very important you learn your equations in physics. So the equation is wavelength equals frequency times by wavelength. In symbol form, v, the wave speed, is equal to frequency f times by lambda, the wavelength. Now here you've got to look at how you can then work out the wave speed. So we can see here that if we work out frequency and we work out wavelength, if we multiply the two values together, we'll work out what the wave speed is. So you would adjust the bar so that it just touches the surface of the water, and adjust the motor to produce a low frequency wave. You then adjust the lamp so the pattern can be seen underneath on the card. You then place a meter ruler at right angles to the wave and then measure the length of a number of waves. So it's important to note that you don't just measure the difference between two ripples, because that's quite a small difference in length, so it's quite difficult to measure. So you can measure the difference in ripples between 5 or 6 of them. So let's say 6, and then we divide by how many waves are present. Now remember, there are 2 ripples to cause one wavelength, so therefore if there are 6 ripples you're measuring in between, you divide by 5 to find the length between 2 ripples, which is then going to be 1 wavelength. You can then count the number of waves passing a point in a given time. Now again, you don't just do 1 second, because that'd be quite difficult to measure. So you count how many waves pass a point in 20 seconds and then divide by 20, which gives us our frequency. You then multiply the two values together and you get your wave speed. Now you can also think about how you can make this more accurate, and for example for the wavelength you could take a picture with your phone and then measure the wavelength that way, but make sure the ruler is in shot. And then for the frequency you could record a video of the waves passing a point on your phone, but once again you should really have the stopwatch in the picture frame so you can work out how long has passed, so you can slow down the footage to count them more easily. Next question. Light is usually described as a wave. Light can also be described as a stream of particles. So these are two different scientific models of light. What statement describes a scientific model? And why do scientists sometimes have different models like the wave and the particles models of light? So sometimes an old scientific model is replaced by a new model. Explain why scientists replace an old scientific model with a new model. Include an example from physics in your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so the first thing to note is a scientific model, which we need to be aware of, is an idea used to explain observations and data. That's what a scientific model is. Now, we sometimes have different models in science to explain different situations, because one model might not be able to explain all observations. And then finally, how do you replace a new model? Now, it's very important you know this, because this is the scientific method. So new experimental evidence or data, which can't be explained by the previous or existing models, or the predictions of the old models are incorrect, so therefore we need to make a new model which can explain the new evidence, or can make predictions which are true in the new experiments. And think of an example of this. So we've got the Big Bang Theory, we've got the plum pudding model, we've got the model of light as such like that. So it's important you know how this particular idea works. So next question. Some students use water waves in a ripple tank to model the behaviour of light waves. Figure 16 shows what happens to the wavefronts as they pass the boundary between deep water and shallower water. Explain why refraction happens at the boundary between the deep water and the shallow water. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to understand how refraction takes place. That's a key idea in physics. So refraction is when the wave changes speed or velocity. Now you'll notice in this example, in this case, the wave is travelling faster in the shallower water. You can tell this because the wave lengths are closer together, so therefore it tells us that it must be travelling faster. Now, as a result, you can say that the refraction is caused by the change in the speed of the wave as it moves from one material or density to another material or density. Now, it's also important to note that the refraction bending process takes place because not all of the wavefront hits the new material at once. So in this case, you'll see that a proportion of the wavefront hits the shallower water first, so therefore they travel slower in that particular wave, that part of the wave. So as a result, it's going to cause that change in direction. So when it goes into the shallow water, it travels slower because once again the difference between the wavefronts is smaller, so the wavelength is smaller, so therefore we know speed equals frequency times by wavelength. So we know for refraction frequency remains constant, so in the shallower water the wavelength is smaller, so the overall wave speed is shorter. So that tells us that refraction will take place because the speed is changing, but because all the wavefront is not hitting the wave at once, it'll not all change speed at the same time, so it will cause that bending or refraction to take place. Now figure 17 shows the wavefronts travelling parallel to the boundary between the deep water and the shallower water. Explain why the wavefronts in figure 17 do not refract at the boundary. So pause the video now, then unpause the video when you want to go through the answers. Right, so again, when you're going from the deeper water to the shallower water, you are going to be going slower in the shallower water. You can see this because the wavelength, which is the distance between the two ripples, is shorter for the shallower water. So because the frequency remains constant, wave speed equals frequency times by wavelength. So if the frequency stays same but the wavelength goes down because the distance between the two ripples is shorter, it tells us that the wave speed is smaller, so it's going slower. But the thing is that the entire other wavefront is going to change speed at exactly the same time because all the wavefront is going to hit the new shallower water at the same time. So whilst the wave is going to be travelling slower, because every point slows down at the same time, the speed changes at the same time, so you don't get that refraction or bending effect. Now, next question. Seismometers on the Earth's surface record the vibrations caused by seismic wave. The figure 3 shows the vibration recorded by a seismometer for one P wave. Calculate the frequency of the P wave shown in figure 3. So pause the video now, then unpause the video when you want to go through your answer. Right, so it's important that you know what the definition of frequency is. So frequency is how many waves there are in 1 second. So the first thing you do is you count how many waves you can see in this particular figure. Now, one wave is when it goes up, down and back to where it starts again. So we can see that there is going to be if you see, we're going to have one wave going from the start to then the second time it passes through the center, then we'll have another wave there, and then we have another wave there, so we're going to be having approximately 2.5 waves. Now the next thing to note is that we have 2.5 waves in 10 seconds. So then how many waves do you have in 1 second? So you can then work it through like that and you get your answer to be 0.4 hertz, because there's 0.4 waves every second, so we can work it through like that. Now, next question. Write down the equation which links the frequency, wavelength and wave speed. Now the P wave shown in figure 3 is travelling 7,200 meters per second, so calculate the wavelength of the P wave. So pause the video now, then unpause the video when you want to go through the answer. Right, so like I said before, it's key and crucial to memorize your equations for GCSE physics. So the equation for this is wave speed is equal to frequency times by wavelength. V is equal to F lambda. Now the next thing is we've got in the previous question that the frequency is 0.4 hertz. We know that the speed is 7,200 meters per second, so we can pop that into the equation. So 7,200 is equal to 0.4 times by wavelength. So therefore wavelength is equal to 7,200 divided by 0.4, because you need to get rid of the 0.4 on the side of the wave then. So to get rid of a division, sorry, a times, you divide. So if you divide on the right hand side, you divide on the left hand side. So it's 7,200 over 0.4, which is 18,000 meters. Once again, you check, does that look sensible? And it could be for a seismic wave. Next question. Figure 7 shows the apparatus a student used to investigate the reflection of light by a plane mirror. The student drew 4 ray diagrams for each angle of incidence. The student measured the angle of reflection for each diagram. Table 2 given the student's results. So for each angle of incidence, the angle of reflection had a range of values. This is caused by an error. Which type of error will have caused each angle of reflection to have a range of values? Then suggest what the student might have done in the investigation to cause an angle of reflection to have a range of values. So pause the video now, then unpause the video to see the answer. Right, so the first thing you've got to understand is that the type of error that causes a range of values to be produced is called a random error. Now, a systematic error is when you get the same error each time, so you won't get a range of values, you'll just get each value out by the same amount each time. Now, it's important we don't use the phrase human error because that's quite vague, because a human could cause either random error or systematic error. So it's this random error which is a different value of error for each particular measurement taken. Now, suggest what that random error could have been. Well, just think of the experiment yourself and what mistake could you make in just one reading which could lead to a wrong value. So not a constant mistake you make in every reading, just a mistake you make for one reading. So things could be you've misjudged where the ray is, you've not replaced the mirror or ray box and put it in the right position, you measured the angle incorrectly because the line was too thick, the idea that maybe the mirror moved its angle so it wasn't at 90 degrees, anything which could practically cause a mistake just once in the experiment. Next question. Estimate the uncertainty in the angle of reflection when the angle of incidence is 50 degrees. And then the student concluded that for a plane mirror, the angle of incidence is equal to the angle of reflection. Explain whether you agree with this conclusion. So pause the video now, then unpause the video when you want to go through the answer. Right, so how do you work out uncertainty? Well, uncertainty is worked out by doing the range of the repeats divided by 2. Now, the range is the biggest value minus the smallest value. Now, we're doing it for 50 degrees. So the biggest value is 56, the smallest value is 46. So 56 minus 46 equals 10 degrees. And therefore, we divide it by 2 because it's from the average up and the average down, so therefore it's the average plus 5 and the average minus 5, so our uncertainty is plus or minus 5 degrees. Now remember, you can only calculate uncertainties in repeats, not just in different values. So you couldn't work out the uncertainty for the 20, 30, 40, 50 for all of them, you just work it out for one row because it's just for the set of repeats. Now, what does the uncertainty actually show us? It shows us where we are certain that the value will lie between. So what we're saying is that we know that for 50 degrees, the average value is 51 degrees for the angle of reflection, but it's plus 5 or minus 5. So it could be anywhere from 56 degrees to 46 degrees. So via that logic, when we're trying to do our conclusion for part 4, we've got to think about that. So it's the indication that for 20, 30 and 40 degrees, the angle of incidence is going to be equal to the angle of reflection when you've considered your uncertainties. So when you've considered the error produced by the random error in the investigation, you can see that it's going to be the 20 degrees angle of incidence is going to be approximately 20 degrees angle of reflection, 30 and 30, 40 and 40. However, you could argue that for 50 degrees that there's a large range, there's a big uncertainty, the precision of the data is not very good, so therefore you could argue that it's not correct for 50 degrees, but once again, it's more about how you use the data as opposed to giving one simple answer. Next question. What extra evidence could be collected to support the student's conclusion? And then state one change the student could make to the apparatus if you wanted to use the same method to investigate diffuse reflection. So pause the video now, then unpause the video when you want to go through your answer. Right, so what extra evidence could be collected? Now it's important to note that carrying out more repeats is not extra evidence, because it's more of the same evidence you've already got. And also you can't change a control variable such as the type of light used or the type of mirror used or the type of paper used, because that's not the same experiment again, so you can't have it as the same conclusion. So extra evidence either comes from having a larger range of data, or by having a smaller interval. So you could say I will go up in 5 degrees by having a smaller interval instead of every 10 degrees, so measure 25, 35, 45, 55, or you could say use a bigger range, so I'll go from 10 degrees to 70 degrees. That will give you extra evidence. Now, how can we investigate diffuse reflection? Well, what we have in this investigation is specular reflection because it's off a smooth surface. However, diffuse reflection is when you have a irregular surface, when it's a rough surface, so you would have to talk about using an irregular reflecting surface. So that brings an end to our revision session today. So hopefully if you've been successful and learnt in today's lesson, you can answer GCSE physics examination style questions, you can assess your understanding of GCSE physics, and you can understand what topics you need to improve upon for GCSE physics. So thank you very much for watching this revision session on GCSE Physics Separate Science Paper 2. Thank you very much and have a lovely day.